Okay, so afternoon, everyone. We're going to start thermal properties and mechanical properties, which is your module 3. Today, we're going to cover 2 sections in module 3, which are basically simplest sections, and one is almost strictly revision. This part 2 here is a lot of revision. All right, so we're just going to follow through, see what we have, and if you have any questions, please ask. Okay, just testing the pens. Make sure they're working. Right, pens working. There's heat. Let's use orange. Right, good. So thermal properties and mechanical properties. Module 3. Moving on. Heat is the form of energy that determines hotness or coldness of a body and is measured in joules. We know this, right? As in, heat is the easiest way we can determine whether we have excess energy or if we are losing energy. That's the very first way we can determine energy in a system, is by the measure or by feeling heat. Okay, continue reading. Temperature is a degree of hotness or coldness of a body, or temperature is how we measure heat. And it's expressed on a given scale. We have several scales that are in use. There is degrees Fahrenheit, which we don't use. That is all imperial scales. So don't bother. We don't do anything with Fahrenheit whatsoever. We have degrees Celsius, which is your metric unit. The metric unit of temperature is degrees Celsius. And then we have Kelvin, which is our SI unit of temperature. We generally use Kelvin in almost all of our calculations when it comes to heat, but there are some places where it really doesn't matter whether we use Kelvin or Celsius. All right, and this we did go through, or you all should have gone through this in Form 5, but we're going to touch on it again anyway. So note that the SI unit for thermodynamic temperature, another name for the Kelvin scale, is the thermodynamic temperature scale, or the absolute temperature scale, is given by Kelvin. Please note, it is not degrees Kelvin. Don't do that. Don't do that. Okay, it is just Kelvin, named after Lord Kelvin. All right, you can go and read up on Lord Kelvin if you want. He did a lot of work in physics and chemistry. Okay, so the instrument used for measuring temperature is the thermometer, which we do know. I hope you all know that by now. Any physical property that varies linearly with temperature can be used to make a thermometer. How can any physical property be used to determine temperature? So let's see. All right, so we want to know, this is basically telling us how we calibrate a thermometer, any sort of thermometer, y'all. Whether it be a liquid and glass thermometer that you all should know, whether it be a resistance thermometer, that's a thermometer where the resistance changes as temperature changes, whether it be a color thermometer, a temperature strip. All right, we can calibrate it. Calibrated meaning we determine where certain values lie. All right, so here you have to know certain topics and certain points in the calibration of a thermometer. And first thing to know of these are your fixed points. All right, you should have done this again, as I said, in CSET, but if not, it's all right. All right, so we have fixed points. So let's read it. First, determine the property at the lower fixed point. The lower fixed point, here you can use PTO, or you can use TO, which is your temperature at a certain temperature, or your property at a certain temperature. Then we have our temperature at 100 degrees. So 0 is 0 degrees, 100 is 100 degrees. And then we'll have T theta, which is your temperature at some given temperature. So whenever you want to calibrate a thermometer, we use this formula and we look at the property. Now you see here, folks, the property P here means a property that we're looking at. There's several properties that change linearly with temperature. All right, one of them could be length, right? Length will be one of the properties that can change with temperature, because when we have a liquid and glass thermometer, all right, liquid and glass thermometer, folks, is your regular thermometer that we have, right? Just with a little thin strip of liquid contained in the thermometer, right? So how they define this, they determine where your length will be at 0 degrees Celsius. Then we determine where our length would be from the bottom, right? Then we determine where our length would be at 100 degrees Celsius. And then if we want to determine where our liquid, which is either alcohol or mercury, will be at some given temperature, we find the distance at some given temperature. So the formula to work out or to start calibrating your thermometer in Celsius, right, or centigrade. Celsius and centigrade means the same scale, so do not get worried if you happen to see degrees centigrade or the centigrade scale. It means the same thing. All right, so we have our first formula to learn today is P0 minus PO divided by P100 minus PO by 100. So what we're looking at whatever property we have that we're measuring for our thermometer, whether it be length, whether it be resistance, whether it be voltage, whether it be current, all of these can be used for your property to determine your temperature when we want to calibrate a scale. Calibrate a scale is just to determine what value represents what, right? Because when they make thermometers, they don't have the drawings and the markings on there. We have to think of them ourselves. So this is our first formula for here, really simple, and remember, it's just going to be the length of your thermometer. Let's rationalize this out. Not this crazy rationalization we're doing the other day, Malik. Let's rationalize this out. If I want to work out what value this is from 0, this is going to be my theta, right? All it's going to be is this length divided by the length from 0 to 100. How easy that is, right? It's really simple, because something at 100, you're going to get nice even intervals. You just divide it out by 100, you know, breaking it up into 100 parts. Okay, so the hardest part here is to remember which one goes on top and which ones goes at the bottom. A little tip to remember, the part at the bottom is just going to be your full scale that you're working with. Right, so let's record, let's check or recall this. The lower fixed point is the temperature of pure melting ice. Note, we never said ice alone. You have to take in consideration, especially those of you all doing chemistry, you should know the importance of proper terminology and proper conditions now, right? So we have pure, meaning no dissolved gases, no chlorine, no dissolved salts in it. It has to be pure H2O, and it must be melting ice. Right, folks who are here, do you know why we use melting ice as opposed to solid ice?
Yes, because melting ice is at 0 degrees Celsius.
Say that again. Melting ice.
Yes, I say because melting ice is at 0 degrees Celsius.
Melting ice is at 0 degrees Celsius. Kind of.
And bluff ice is like 4 degrees Celsius.
All right. Okay. All right. Everybody here is doing chemistry, I think. Yeah? I'm not doing chemistry, I think. Curve one. No, curve one doing chemistry.
No, Miss, I don't think we're doing chemistry.
You're not doing chemistry.
You're not doing chemistry?
We're not doing chemistry.
All right.
Is it because all that heat's going to melt in the ice and not into the lattice?
No. All right. Why we want the temperature of pure melting ice? This is what happens. Where can I pop in a new slide? New slide. Right. So, Right. So what we have, when we have a container, say of ice, like ice blocks, right? What happens, even though think that we look at macroscopically, and these are small ice chips, you see this little air pockets we have in between. These air pockets will not be 0 degrees Celsius. All right, all of these air pockets might be some temperature above 0 degrees Celsius because air is a very, very poor conductor of heat. So we don't want to come and take and put our thermometer in that right, in that, right, inside of here, because it can hit or be on the side of a thermometer and not side of a piece of ice and not actually getting the temperature of the ice. So what we tend to do, we will go and use a container. Usually it's a funnel. Right, so that's our funnel attached to a retort stand, right, with crushed ice that is melting, right? Why are we using crushed ice, like, you know, snow cone ice? We use crushed ice that is melting because at this point here, all of the melted water, right, all of the melted ice will be water and it will be taken up, right, the fine spaces in between. So everywhere where we have a fine space, there will be water that is nearly or basically at 0 degrees Celsius. So it doesn't matter where you put your thermometer is not going to be hitting air spaces like here. These air spaces, no. Where you put your thermometer in here, because it's crushed ice, your thermometer is easily going to go in, right? And you'll be able to record the temperature of your ice. Now, why do we put it in a funnel? We don't want this to melt and become a container of water. We just want enough melted water in there to take up all the air spaces between the crushed ice cubes, right? Or the crushed ice. So what this does, we just have the excess water dripping out, right? But there's still enough water in between, in the particles, in the ice, small little crushed ice to remain here. So we always, when we want to find the temperature of 0 degrees Celsius, we must use a mixture of crushed ice and water. Why do we have water? Because we need to get rid of those air spaces that will be more than 0 degrees Celsius. Why? Because air is a poor conductor of heat. All right, so if they ask you why we use certain things, this is why we use what we have to use. So going back up to here, the upper fixed temperature is the temperature of steam from water boiling at normal atmospheric pressure taken at 100 degrees Celsius. Note they are telling us to come and take the temperature of the steam of the water. They're not telling us to put the thermometer in the boiling water. Anybody knows why we would come and say this is our boiling water here, these are water boiling. They're going to tell us to take our thermometer and put it in the steam right above the water and not in the water. Anybody wants to make a guess, or let's rationalize this out. Think about this from physics and chemistry point of view. Why would we put the thermometer in the steam and not the water?
Is it because the thermometer would be exposed to liquid and gas?
No. Thinking about what happens to water when it boils. How do you know when water is boiling? It's a real obvious question.
It will be like a rolling boil. You see
Yes,
bubbles.
we will see bubbles, right? Do you think those bubbles are at 100 degrees Celsius?
No, ma'am.
I am making you question your life right now. What you've learned in life is not correct. Well, it's been so simplified, it's not correct. What happens when we have water that is boiling? We have what we call a rapid boil, and this is due to convection currents, right? This is again revision. See how everything is revision, what you did from 4 and 5, right? This is a convection currents is when we have heat at the bottom and cool at the top, meaning we have a constant changing temperature of water as that water boils. So do we want to put our thermometer in something that is constantly changing temperature? We don't want to do that. But what we can do, we know that water at regular pressures, right, being at 1 atmosphere, all right, so when we take the temperature of water, when water is at 1 atmosphere, the water will boil at 100 degrees Celsius. And when water boils, it makes that transition state from liquid to gas, right? So that means that the gas molecules that have just left our water is 1 at atmospheric pressure, and 2, they will be at the temperature of the boiling water. And because these molecules are not circulating, they're just being let go from the liquid, we can take our thermometer and put our thermometer in that active steam level or that active steam part. So we take our thermometer and we put it in the active steam part. So we put it like right here in the steam itself, not in the water. And we will be able to measure our temperature, which is 100 degrees Celsius. All right, so there's no such thing. If you were thinking, if you wanted to calibrate a thermometer or to determine your fixed point, you have 2 things to do to determine your fixed point. 1, to get your lower fixed point. You only get your lower fixed point by putting a thermometer in a mixture of ice and melting water. And 2, to get your upper fixed point, which is 100 degrees Celsius, is to put your thermometer in the active steam region just above your boiling water. All right, so if you had come and said that you took the temperature of ice and then you took the temperature of boiling water, that wouldn't be true. All right, because let's look at this at another point of view in chemistry. That's in chemistry point of view right now. What will lower or raise the boiling point of a liquid? The presence of what?
Impurities.
What? Say that again?
Impurities.
Yes. Impurities will change the boiling point of my water, right? It will either lower it, well, most likely it does lower it. And let's think about what we have in water. We have a whole bunch of minerals dissolved in water. We have calcium, we have chlorine, we have dissolved gases, right? We have a whole bunch of things dissolved in our water, and that is not pure water, meaning it will not boil exactly at 100 degrees Celsius. You don't come and say, but miss, it's close enough. No. When we want to calibrate something, we have to be on the point exactly where we need to be. So steam is steam. When you boil water and create steam, you are getting pure water coming out from that steam. That steam is without chlorine. It doesn't have calcium in it. It would have lost the carbon dioxide. It would boil off the oxygen and the nitrogen. And that's how we end up getting distilled water and pure water, is by boiling off and condensating steam. right? So we don't use the boiling water because water has a lot of changing properties to it. One, it's constantly changing temperature because it's going through convection currents, and two, it has impurities, right? And there's no way you can guarantee that water is pure unless you made it yourself by the same process of condensing steam through a distillation setup. All right, so rather than go through all of that, let's put it to one time, the steam, the very hot steam. Going on. All right, the work example is really, really simple. All right, I don't think I need to go through this in depth, but we'll just skim through it really quickly. A mercury laboratory thermometer has a mercury level of 5 centimeters above the level at the bottom of the bulb at the ice point. So we already know where the ice point is, or our lower fixed point. And at 25 centimeters for your upper fixed point. So we know that the distance between these two, the lower and the upper, is 20 centimeters. And that 20 centimeters is going to represent 100 degrees Celsius. All right, so we want to determine what temperature, what will the temperature be when the mercury level is 17 centimeters above the base of the bulb. So what we need to do, we can't just go and measure from the bulb itself. We have to measure from where we start, which is at 0. So this is where we use the formula to get your temperature in degrees Celsius. It's going to be our property at theta minus our property at 0 divided by our property at 100 minus our property at 0 multiplied by 100, right? Because this is going to give you a fraction. What's our property at theta? 17. What's our property at 0? 5. What's our property at 100? 25 minus 5. So we're going to end up getting 17 minus 5 is 12 over 20. I don't even need a calculator to do that. 12 by 5 is going to give you 60. Employ a little bit of shortcut in maths. Tell me if you all got that. You can do that really, really quick. You get that?
Yeah, miss.
Yeah, so easy that was. So we can calibrate any thermometer using this formula. Any single thermometer that has values to read, we can calibrate and work out what the temperature is without having to go and make markings and stuff like that. Right. When different thermometers using different properties are used to measure the temperature of the same object, different values on the centigrades are obtained. This is because different properties vary differently and are not necessarily linear. What is a linear scale? A linear scale is where we have a straight line measurement where you can get an exact value for every single point and a very predictable value for every single point. Now, when you end up using something that is not linear, you will not get something that is very predictable. All right, so let's continue reading. These temperatures depend on the physical properties of some substance, and these scales are empirical scales. It is necessary to have a temperature scale that does not depend on the physical property of any substance. This scale is called the thermodynamic temperature scale, otherwise known as the Kelvin scale or the absolute scale, right? As in what they've come up with before, they used to look at the temperature at which, you know, something boils, the temperature at which something melts, the temperature at which something freezes. Now, using different materials, you're going to get slightly different temperatures owing to a big thing called impurities in materials. So they had to come up with a different way to measure or to classify temperatures. And what they did, they came up with, by Lord Kelvin, the absolute temperature scale, or the thermodynamic temperature scale. That's the actual scientific name for it. And as the Kelvin scale, we're going to go through Kelvin scale really simple. This is a theoretical scale, meaning it was done via mathematics. That does not mean that's theoretical in guesswork. Please be reminded that a scientific theory is much different. Is it really bad? It's pouring. Right. So a scientific theory is much different to the regular word theory. So in this means a theoretical scale means it's been run through the scientific method, and it's basically a fact typical. So it's a theoretical scale that has one fixed point. There's only one fixed point of the hold on for a second. So the theoretical scale has one fixed point, only one. And that one fixed point is called the triple point of water. Chemistry students, you all know what the triple point is. Well, I hope you do, because I learned this in chemistry in A-level school. Right, the triple point of water is the temperature at which water, ice, and water vapor are in equilibrium. This temperature is found to be 273.16 Kelvin. So this is our triple point to remember. So your triple point temperature is 273.16 Kelvin. Of course, we're looking at pure water, but at this temperature, your three states of matter can exist simultaneously. Any part, anyway, above and below this, we only have two points that exist at the same time. Right? If we go below the 273, we're just going to have ice and water vapor. If we go above the 273, we're just going to have water and water vapor, or liquid water and water vapor. Right? So the temperature on the Kelvin scale, continue reading, the temperature on the Kelvin scale is given by T is equal to your property at some given temperature divided by our triple point, whatever property we are, right, a triple point multiplied by 273.16. And this is how we can come up with our conversion scale. You all should notice the temperature in degrees Celsius is given by taking, let's write this down in a not so confusing manner, is your temperature in Kelvin minus 273.16. Remember at Form 5, we said that it was just 273. We use 273.16. Please note that the ice point on the Kelvin scale is 273.15. So we have a little teeny tiny little difference, right? As soon as we drop down from 273.16, we turn into ice, right? So the ice point we don't use, we take our triple point of water. The slight difference occurs because the triple point is determined at very low pressure and where all gases are driven out of the water. But we're not going to fuss too much on that. Just clarifying it. Types of thermometers, just learn them because these can come from multiple choice, so they can ask you to list some types of thermometers. So we have liquid and glass thermometer, constant volume gas thermometer, a resistance thermometer, a thermocouple, an optical pyrometer, right? If you want to know any more on these, look them up. Right? Liquid and glass thermometers, basically the thermometers we've known our entire lives. We have two types of them. We have mercury and alcohol. Mercury responds very well, but the problem, mercury tends to be expensive and toxic. Alcohol, it's cheap, but hard to see, so you have to color it. But problem with coloring it, you end up changing some of the properties of the alcohol thermometer. So you have to go and readjust for it. Water is never used because water takes too much time to respond to heat. right? Really, really takes too much time and it doesn't always expand linearly. All right, so you all can go through this, the comparison between our two types, our thermometers actually. But one thing I should ask you to do for exams, make sure and know what are the properties and ranges and stuff of your liquid and glass thermometers. All right, we'll go through them, easy reading, see what they are. Right, you're not really supposed to know the advantages and disadvantages of all the types of thermometers, but let's read through it to make sure you have some sort of knowledge in the back of your head. Properties of thermometric liquids, you all can read this. The temperature range of mercury is -37 degrees Celsius to 357 degrees Celsius. So what this is good for, this is for relatively high heats, as in temperatures that we will be exposed to. But -39 degrees Celsius, there are places on this planet that are regularly colder for months at a time than -39 degrees Celsius. This is where we will tend to use an alcohol thermometer. An alcohol thermometer is really good in measuring very cold substances, but not very, very cold, not very cold, right? But obviously not good enough to go and measure things like boiling water. When you want something that is far above this, is where we tend to use resistance thermometers, right? And whatnot. Those should be in the table above. So know the ranges or the general ranges of mercury thermometers and alcohol thermometers, and know why one is good for something and why the other one is suitable for other purposes. All right, mainly what I just highlighted for you. One, it's not good for very cold, it's okay for pretty hot. Next one, it's good for very cold. You all can read this. These advantages and disadvantages you can just read. There's nothing too much to go through. It's in the handout. Disadvantages, please read them and understand them. Everything here, you should grasp the current physics knowledge you have. Why water is not used as a thermometric liquid. One, water is colorless, and wet glass, so the meniscus in the glass is difficult to read. You all know that water is difficult to read. The meniscus in water is difficult to read at sometimes, right? It has a really small range to work with. You want from 0 to 100, as in it will not go above 100. So it's not even good to measure like steam, because steam can be heated to above 100. It's not good to go and measure things that are below freezing point, right? It does not expand uniformly. See this one here automatically kicks water out of consideration when it comes to thermometers. It evaporates and condenses in the tubing, and there's a high specific capacity. High specific capacity means it takes a while to respond to heat, right? Mercury is a metal. Metals respond to heat almost instantaneously. Alcohol, in this case, because of the nature of alcohol and because it's a volatile liquid, it responds to heat very quickly. Water, on the other hand, will sit down and take its time. So all these are reasons why we don't use thermometers, use water in our thermometers. You know, you would think there's a cheap liquid, it's everywhere, we could get one. No, it's one of the worst things to use. Clinical thermometer, you all can read that. Constant volume gas thermometer. These are generally found in industry. You'll never find it in a small scale setting because it's a big set of apparatus. So you read it through too. Yeah, this you can just read through advantages, disadvantages. Same thing for the resistance thermometer. All right, what a resistance thermometer is, the way how resistance is set up is you all simply, if I have a resistor and I were to measure the voltage and measure the current of that resistor, right? If I change the temperature of my resistor, or if I change my temperature, my resistance can go up And if I go too hot, my resistance will go up. If I go too cold, my resistance will go down. All right, and let's just think about it. Electricity and resistance go hand in hand. Resistance is what prevents the free flow of electrons. And if I have a whole bunch of erratic, energetic electrons, my resistance is going to be high. And on the flip side, if I have a whole bunch of nice, cool, calm, not moving too much electrons, right, my resistance is going to be low because nothing is stopping these electrons from flowing. So the nice about resistance, it's a linear relationship. So you can determine what temperature is by just looking at the resistance. And this is what we tend to use a lot more in industry because it can go up to pretty high temperatures because we could use metals that have very, very high melting points. And then we can go up to ceramics, which have even higher melting points than metals. All right, so you all can just read through them. And I think that's going to be it for this handout. That's the different type of thermometers. All right, so read through them, see what they are. That's the make a little short note on that and read how they work. You just want to know, one, their basic operation, two, their advantages and disadvantages, right? And three, their temperature range. That's what you should know generally when it comes to heat and thermometers. All right, so we'll stop sharing there for this part. And then we're going to go on to measurement of heat. All right, so does anybody have any questions regarding what we just did for thermometers? And anything in the thermometers? If you remember, it's only two equations that we have, really two. No questions? Can we move on to the next section then?
Yeah, miss.
All right. Moving on, measurement of heat. All right, so measurement of heat. Again, you will know most of these terms, if not all. Measurement of heat, we're going to look at heat capacity, specific heat capacity, and latent heat. All right, so the heat capacity of a body is defined as the heat required to raise the temperature of a body by 1 degree Celsius or 1 Kelvin. What you should know that the change in temperature in Celsius and change in temperature in Kelvin is the exact same thing. If you don't remember doing that, we'll go through it in a bit. All right. It is expressed in joules per Kelvin or joules per Celsius. Does not matter. All right. For a particular substance, heat capacity. Heat capacity, this is where we're going to go a little bit different. Heat capacity is equal to mass by specific heat capacity. Here we didn't know that in Form 5. We're looking to connect these two terms. Heat capacity is a really vague term. Specific heat capacity, you know, they took out the word, is more specific. So let's read specific heat capacity. The specific heat capacity of a substance is the quantity of heat required to raise the temperature of a unit mass. Anytime we see unit of anything, we're talking about 1 in the SI unit of that substance. So if I say unit length, we want 1 meter. Unit resistance, 1 ohm. So the temperature of unit mass or 1 kilogram of the substance by 1 degree Celsius. So here we're going to have our equation, energy. Energy in heat is given by 3 letters. We're going to look at Q, which is heat. We're going to look at U, which is internal energy. And we're going to look at work, which is the work done by your, usually for your gases. So you're going to see heat expressed with these letters, not E as we learned in Form 5. Right, so to learn it from now, the heat generated in a body by heating, where we add heated, is given by the letter Q. So Q is equal to MC delta theta. Is usually Q is equal to MC delta theta. I don't know why they left out the delta. Right, where delta theta is your change in temperature either in Kelvin or Celsius. Your mass must be in kilograms. Your specific heat capacity is in joules per kilogram per Kelvin, right? And change in temperature, that's just the change in two numbers. It'll give you the same thing. There's no need to convert Celsius to Kelvin when you will find any change. Now, if you multiply temperature by something, that's different. But change in temperature, it doesn't matter what scale we use. Anybody wants me to go through why it doesn't matter if we use Celsius or Kelvin for change in temperature, or are we okay with that?
Just repeat the question, please.
Do you want me to go through why the change in temperature could be in Kelvin or in degrees Celsius?
I think I'm okay with it.
All right. You okay with that? Shaniqua, Jayan, you okay?
Yeah, miss.
All right, okay, good. Let's move on. Determining your specific heat capacity of a solid using method of mixtures. If you recall, method of mixtures is where we take a hot substance, mix it with a cold substance, and you get an equilibrium temperature, and we're able to work out our specific heat capacity. That's basically what it is. We take a hot substance of unknown heat capacity, mix it with a cold substance that we do know the specific heat capacity of, right? And then we are able to work out our specific heat capacities. So here we have a simple one. This is the one we would have done in school if it was pre-COVID. All right, generally you would have done this in schools if it was pre-COVID. All right, so what you do, you take a container of, say, cold water, right? Water is one of the easiest materials to work with because we have so much of it. We know the specific heat capacity of water, which is 4,200. You all should remember this number from Form 5. Joules per kilogram to Kelvin. All right, you should remember that from Form 5. All right, so we know what the heat capacity of water is, the specific heat capacity that is. We take a hot object, right? So we take that object and put it in a water bath and heat it. Why do we put something in a water bath? Right? We don't just take a hot object and put it on fire, right? Because number one, it's going to heat up too much and it's going to heat up unevenly. If you take a piece of metal and you place it directly on some fire, what's going to happen? The bottom is going to get very, very, very hot, right? And the top is going to be relatively cooler, unless you leave it for some degree of time, and then you run the risk of burning and melting the things that are attached to it. So we don't want to heat objects directly on a flame. We use what we call a water bath or oil bath. Yeah, water bath or oil bath. Oil bath is a big hint for upper 6 lab. Have a lab that would have an oil bath, right? Where we can apply heat to that water, and we know the maximum temperature water can ever reach at regular conditions are 100 degrees Celsius. So we can let the object sit down in the boiling water for a few minutes. And by having that object sit down in the boiling water for a few minutes, that object is now going to be true and true, as in completely 100 degrees Celsius. All right, so we take this hot object where we know it's 100 degrees Celsius, we put it into the cold water, we kind of stir it around a little bit, and then we could record the temperature of the water. Now let's go to see why we're doing this. We all know if you take something hot and mix it with something cold, our temperature is going to drop. Correct? You have to give me thumbs up and thumbs down Yes or
Yes.
no? You don't have to reply all the time. Good. Right? We know this from regular common sense or from regular life. How many of us boil, drink tea that's too hot and put 2 ice blocks in it? Right? Same thing here. So let's just go through it. The procedure, the solid is weighed to find its mass and then suspended by a piece of thread and heated in boiling water. And the temperature of the boiling water is recorded. We measure the temperature of boiling water. We don't assume that our water is boiling at 100 degrees Celsius. Unless we are at perfect conditions and we have pure water, we cannot assume that water boils at 100 degrees Celsius. Moving on. A calorimeter and stirrer are weighed. Now, a calorimeter is a double-walled container. Right? What it is basically a pot in an next pot. Right? A little aluminum pot or usually copper too. Right? And it's filled with cotton. That's regular cotton. And what this cotton does, it provides insulation. Right? So if you pour something inside of here, the temperature is going to remain pretty much stable for much longer than if I had just poured hot or cold water in a regular cup. Right? It's a really, really simple setup. It's simply 2 aluminum tins, right, with some cotton. There's a fair amount of space here. It's usually, for the ones we have in schools, about at least 1 centimeter or 2 centimeters across where we can put cotton around it. So we insulate it. So that's why we use calorimeters, because they're well insulated, or the next word for insulation is called lagging. Right? Lagging here means to insulate. So let's continue reading. The calorimeter and stirrer are weighed, and when half filled with water, to obtain the mass of the water. Yeah, you weigh this empty, then you weigh it with water, and you can get the mass of your water. The initial temperature of the water in the calorimeter is taken and recorded. The solid is then quickly transferred to the calorimeter, and the water is gently stirred. You all can see where we're going to have some energy losses happening, right? The highest steady temperature reading on the thermometer is then taken and recorded. Calculations. 1, assuming there is no energy loss. We already can see that there is some energy loss because we're taking that hot object and transferring it into the calorimeter. The mere fact we're taking that hot metal out of the water, out of the hot water, passing it through air, right, and put it into something else, it's going to lose a couple degrees of temperature. Right, but we still assume that there's no energy loss. Right? Okay, they mixed this up here. I will fix this. Right? There's no energy loss. What we're going to assume, that all the energy from the hot object is used to warm the cold water. Right? So if you want, you can say all that the from your hot object, right, warms the cold water. Moving on. So we have here is an easy workout. It looks long and complicated, folks. It's not. All right, let's just go through this. Let me add in the next slide. All right, so add the next slide. So we have here the mass of the solid is M1, mass of the calorimeter and stirrer, MC, mass of the calorimeter, stirrer, and water, M3, because we have to take in consideration that the calorimeter can absorb some heat. Sorry. All right, we have the initial temperature of our water is theta 1, the temperature of our hot object, which is the temperature of your boiling water, is theta 2, and the highest steady temperature of the mixture is theta 3. So you're going to have here the energy heat lost by the solid is equal to the heat gained by the water plus the heat gained by the calorimeter. Let's check and see. Let's do our maths. If I have my hot object here. All right, this is my calorimeter. Put some light cotton in it. And it has some water in it. Right, it has some cold water in it. Well, it's not plenty water, but it's enough to be comparable to your object. So what's going to happen? If I have my object, which is mass of my object, my temperature of my object, and my specific heat capacity of my metal. Let's put M. All right, these are our three values. We know what the mass of our object is. We know what the temperature of our object is. We're trying to find this one here. Now, what we're going to do, we're going to take that object and we're going to put it into the water and get a whole new mixture. All right, so let's look and see what we have on this side here now. We have water to deal with. We have the mass of water. We have the temperature of water. We have the specific heat capacity of water. All of these things we know. We know heat capacity of water is 200. You measure the temperature of the water. We tend to use really cold water, right? And we have some mass of water. And then we will have the mass of the calorimeter, which we can weigh on a scale. We are going to assume that the temperature of the water is the temperature of the calorimeter. So that's going to be the temperature of the calorimeter. And the specific heat capacity is going to be the heat capacity of the material that the calorimeter is made out of. Usually calorimeters are either made out of aluminum or copper. So this is what we have here. On one side, we have our hot. Oops. We have our hot side, right? And then on the next side, we have our cold side. So all of this here is the cold. So when I take my hot object, and put it into here, two things are going to happen. One, my hot object is going to cool down, right? And then on the flip side, that energy lost by my hot object is now going to go and warm up both water and the calorimeter. So we have a simultaneous motion of heat. One goes hot and one goes cold, and none is lost. Are you okay so far, everyone?
Yes.
Yeah.
Yeah, man.
It's a simple derivation, you know. It's just because at Form 6 here, we introduced the calorimeter, which we have to take into consideration because this is part of our game, right? So what we're going to say, energy lost is equal to energy gain. Who is losing heat? It's going to be my hot object because that's going to cool down. So that's going to be mass of my object by C of my object by delta theta of my object. And that's going to be energy gain. Which part here is going to warm up? My calorimeter is going to warm up and my water is going to warm up because I just put something hot in both of them. Right? So now we're going to have our mass of our calorimeter by our specific heat capacity of our calorimeter by the change in temperature of our calorimeter plus mass of our water, because remember energy is equal to mc delta theta. We're just using this over and over and over. Mass of our water, heat capacity of our water, delta theta of our water. Y'all, if we know all the temperature changes, as we know what theta M is, we know what theta W is, we know what theta C is. I know what M is. I know all of these terms. Look how easy this is going to be working out. If you want to work this out, this is essentially going to be A by, okay, X by C is equal to A plus B. That's how easy this is when you all boil it down to actually working out numbers, because we know what M is, we know what delta theta is, and we know all of these terms. This here MC delta theta is A. MC delta theta here is B. And to get your C, it's just going to be A plus B divided by your two terms, which are, we could do a question, we'll do a question, don't worry. This term and this term. Right? So this long contrived piece of equation over here, doesn't that look a little scary? I think it does look a little scary. This long equation here can be broken down and simplified to saying C is equal to A plus B divided by X. Simple, simple. You add the two heat energies and you divide by the coefficient of C. Make life easy. All right, so we'll try a question. All right, I'll probably leave a question for you all to do. All right, or I'll send one in and you all can give it a try. So let's just move on. So please, please, please don't worry. This is not as complicated as it looks. It's just because there are a lot of moving parts in this question, but it boils down to A plus B divided by X. Easy and easy. All right, so moving on, precautions. You see this? Precautions. 1, shake the solid well to free it from droplets of water before transferring it to the calorimeter of water. Anybody want to guess why?
That would add to the heat capacity.
Yes, very good. Because you are now going to add to the mass of the water that we're not considering. You see these little water droplets are going to make a difference. Suppose you have a whole bunch of little water droplets on here, and now you put it into a container of water. We are going to change our M. Our mass of water is going to change, and we're not taking that consideration. All right, so 1, you're gonna shake the solid to free it of water droplets. But look at the trouble here. If I'm shaking my object to get rid of water droplets, wouldn't that kind of cool it down? Thumbs up or down? Right, and when I want to cool down something, right, you kind of shake it pretty fast. Right, so by shaking it, you're gonna kind of reduce the temperature a little bit, but you know, you want to minimize these energy losses. The calorimeter should be well laid with an insulating material such as cotton wool. Right, and the mixture is stirred continuously and steadily. That's why we have something called a stirrer in it. If we go up our slides, you're gonna see we have a stirrer. So the stirrer is just mean you gently stir it around to make sure that the temperature is evenly distributed through your system. All right, moving on to okay, that's what we just did, same thing. We have the electrical method, which I will encourage you all to read. Try it yourselves, right? And here we just use a little bit of electricity, right, to work out our stuff. So basically what we have our object, it's connected to a circuit. We know if we could run electricity through a metal, that metal is going to heat up. So we have an electrical heater and we have a liquid. Now we usually use electrical method for liquids because we can work out how much heat it takes to warm our liquid. Right? So you'll go through this. It's the same working as the other one. Just here we use power or we use energy, right? Just recall, if you all forget your energy and electricity, you know that that power is equal to IV. You all know this, right? And we know that energy is equal to power by time. Coming from the equation, power is actually equal to energy over time. So if I want to get my energy is simply going to be my power multiplied by my time. Because you all know when we put on the microwave or we heat something up in an electrical heater, it has to run for some time. So the longer you run it, the hotter it gets. So by multiplying the power by the time, we will get a large amount of energy being supplied to our system. And power is calculated current by voltage. Other than that, is the same working as we just did before. Check it and see. All right, I'll include a word calculation for you. I'll send a couple of word calculations, a couple of word examples. If not this evening, tomorrow morning. We have the calendar and Barnes method. This has never come before. And remember what I told you, things that have never come before, the chances of them coming greatly increase every year, right? Especially at CX, we did get some new questions and not relying on the same questions over and over, right? But we'll see when they release broad topics if we're going to be thinking about this. Just give it a read through, they're not hard and whatnot. All right, it's a simpler equation where you're just working out heats and energies. So we'll go through some questions. There's some questions here to try. All right, I do encourage you all to give them a go. All right, we can do the questions the next day once you have, kind of digested what we have. All right, let's see what we have left. We have melting. We have cooling curves. We have pressure and melting points, latent heats, and whatnot. Okay, so I know we've been running for a while. Do we want to at least do out melting and stop? Tell me what you all want to do. You want to stop here or go through melting and latent heats?
We can finish it.
We could finish. It's been kind of long. Okay. Anyone else? You okay for stopping right here and we'll continue our next day? Nobody? Okay. Nobody else? I'm gonna stop here. All right. So we're gonna stop at melting. Write that down. Okay, stopping at melting. So the next day, since I don't think anybody here is celebrating Eid, so we could run a class on Monday, right, where we will finish this out. This won't take long because we've, kind of broken the back on it. We're going to finish this out, and your choice. You're going to speak for your essay class. You all want to do all the questions in this handout and a couple extras on Monday. You just want to move forward with some notes, and then we hit questions up for a solid week. Monday, do we do just notes, or Monday do we finish out this handout and do questions?
So we can finish with the handout and then questions.
Finish out the handouts and then do some questions. Everybody okay with that? Okay. All right. To be somebody else answer. All right. So let me stop share. All right. So Monday, I will tell you what time we could run a little earlier since it's our holiday. We can do something else with the holiday. Now, if you all have an issue with having something on Monday, again, remember, it is recorded, so you don't have to be here live. If you can't make it, that's fine. You'll see it anyway. All right, so we can run this a little earlier, probably like 1 o'clock or something on Monday. And we will finish this out, and we could probably start the next handout, and we'll do some questions. All right, but for your own benefit, please try the questions in this handout, all right, that you all have it at home already. Give them a try and we'll go through them, all right, really quickly. And then we're going to start, I'll throw in a couple exam questions for you. All right, so folks, let's stop the recording here.